Welcome back to the lecture on differential equation. I'm going to talk about Wronskian and fundamental set of solution with an example, and then I will show how do we actually understand the Wronskian of a differential equation even if we do not know the solution. So the first thing is that if we know the solutions, or if we somehow know that some functions satisfy the differential equation, whether they form a fundamental set of solution. So remember, it is because that some function can more than one function can satisfy your differential equation, but that does not mean that this will form a fundamental set of solutions. So here I have e to the power minus 2x or minus 2t and e to the power minus 3t, and I have a differential equation y double prime plus 5y prime plus 6y, and where prime denotes differentiation with respect to t. And we first going to check that whether y is a solution or not. So in order to uh, form a fundamental set of solution, first this has to form, or first has this to be a solution. So I take y e to the power minus 2t and I substitute here. I can substitute directly y. Then I need y prime and y double prime. So I calculate y prime, which is negative 2, and y double prime, okay. Then you can substitute into the equation. Y double prime is 4 e to the negative 2t plus 5 y prime, so 5 times negative 2 e to the negative 2t plus 6 e to the minus 2t, and I'm going to check whether this is going to be 0 or not. I can see here in the middle term is negative 10 e to the power negative 2t. The last term is as is 6 e to the minus 2t, and the first term is 4 e to the minus 2t. Okay, and I see that this equals 0. 4 plus 6 is plus 10, and then you have negative 10, so that get cancelled out. So e to the power negative 2t is a solution. So let's check e to the power negative 3t whether this is also a solution or not. So y prime, you differentiate y, okay, then you take the second derivative, which is okay. So now you substitute into the given differential equation. So y double prime is just 9 e to the power minus 3t plus 5 negative 3 e to the power negative 3t plus 6 e to the power negative 3t. And again we see that 9 e to the power negative 3t minus 15 e to the power negative 3t plus 6 e to the power negative 3t, and is 0. So we have ensured that e to the power negative 2t and e to the power negative 3t are both solution of the differential equation. Now we are going to check the Wronskian. So Wronskian of e to the power negative 2t and e to the power negative 3t. Okay. So you form the first row of the determinant or of the matrix. If you form a matrix, you take the determinant, so it doesn't really matter whether you form a matrix or determinant. And The second row will be the derivative of the first row. So negative 2 e to the power negative 2t, which is the derivative of e to the power negative 2t, negative 3 e to the power negative 3t, and then you calculate the derivative. So just a cross multiplication, negative 3 e to the power negative 2t e to the power negative 3t. So cross multiplication this and that, negative 2 e to the power negative 2t negative 3t, and evaluate that. First term you get negative 3 and second term you get positive 2, so negative e to the power, in both case negative 2t and 3t becomes 5t, and which is not equal to 0. Okay, so in this example you have seen that how to check a function is a solution of a differential equation or not. You simply take the function and then plug into the differential equation, check whether it satisfies or not. So this way you collect or you get some function. So a second order differential equation, you would expect two solutions. Then in order to determine whether the solution you have found or in your set forms a fundamental set of solution or not, you calculate the Wronskian. Hopefully the idea is clear. So let's look at another example. Excuse me. So in this case, x to the power half and x to the power minus half set of solution, fundamental solution set of the differential equation is 2x square y double prime plus 3x y prime minus y equals 0. So in this exercise, prime denotes a derivative with respect to x and y is a function of x, and I have given two functions, x to the power half and x to the power minus half. So what I'm going to do is, first I'm going to check as before whether they form a solution. So you differentiate y prime half x to the power negative half, y double prime is half times negative half e to the x to the power negative 3 over 2. Okay, so 2x square times y double prime. So y double prime is negative 1/4 x to the power negative 3 over 2 plus 3x times y prime is half x to the power negative 1 over 2 and minus y and x to the power half. Then if we evaluate, the first term is going to be negative half x to the power 2 minus 3 over 2 is half plus 3 over 2 x to the power 1 minus half is half and x to the power half. And you can see that negative half and 1 forms negative 3 over 2, and then you have 3 over 2, so that get cancelled. Then the next one is x to the power half, x to the power minus 1. First one is x to the power half, next one is x to the power minus 1. So that one is going to be minus 1, x to the power minus 2 is y prime. Y double prime is minus 1 minus times minus 2 x to the power negative 3. So 2x square times y prime, which is 2 x to the power minus 3, and plus 3x times y prime, which is minus x to the power minus 2 minus y, which is x to the power minus 1. And the first term is 4x to the power minus 1, second term is negative 3x to the power minus 1, and then x to the power minus 1, and then see it is 0. Okay, so the given functions are solution. Now you calculate Wronskian. X to the power half, x to the power minus 1. Write down the solution in the first row, or the functions in the first row. Then second row will be the derivative of first row, minus 1 x to the power minus 2. Okay, and then cross multiplication, x to the power half times minus x to the power minus 2 minus half x to the power negative half times x to the power negative 1. So negative x to the power negative 3 over 2 negative half x to the power negative 3 over 2, and then negative 3 over 2 x to the power negative 3 over 2, and this is not equal to 0 if x is greater than 0. So then we have a fundamental set of solutions for this differential equation in the interval x is greater than 0. Okay, so hopefully this is now clear what you are going to look for when you want to check a set of function forms a fundamental set of solution or not. So a set of function for a second order differential equation, you would need to have a set of two functions. First, you verify that each function is a solution. Just plug into the differential equation and check whether you get a 0. And then the second point is you check the Wronskian and then figure out whether the Wronskian is not 0. Okay, Wronskian has to be not 0. Then you know that this is a fundamental set of solution. So now I'm going to walk through something that now we want to calculate the Wronskian. So I have a differential equation x squared times y prime minus x times x plus 2 times y prime plus x minus 1 times y equal to 0. And I want to find the Wronskian of this differential equation without solving this differential just use the short form DE. Okay, so if you know how to solve this differential equation, then you know the solution, and then you can find the Wronskian. And if you have found a solution, you actually don't perhaps need the Wronskian, but still for the sake of calculation, whether your solution is found correctly or not, you can calculate the Wronskian. Is one way to at least to make sure that you have found some functions that form a fundamental set if Wronskian is not equal to 0. But now the solution is not known. All we know is the differential equation. Okay. So to determine the Wronskian, I'm going to assume that y1 and y2 are two solutions, two linearly independent solutions. I don't know what is y1 and y2, but this is a second order differential equation, so I know that it has two solutions. So then both solutions must satisfy the differential equation. So I can just copy it. Okay. So y1 satisfies the differential equation, then I get an equation for y1. Also, y2 satisfies the differential equation, so you can write y double prime 2 x times x square and then y prime 2 times x plus negative of x times x plus 2 and plus last term. Okay, so you see that this is the differential equation. So y1 is the solution, so you replace y with y1. y2 is a solution, you replace y with y2. Okay, so now we need some algebraic manipulations. Let's call this equation 1 and this is equation 2. So I take equation and multiply this with negative y2, and then I take equation 2 and multiply this with y1, and then I add them together. So if I do this, then I will get rid of the last term. Okay, and I will combine both of the equation. So let's write down after multiplication. So x square y double prime 1 and multiply by y2. That will be now plus x plus 2 y prime 1 times y2, because I'm multiplying with negative y2. Negative x minus 2 y1 times y2 equals 0. 0 multiplied by y2 is 0. Now I'm going to take the second equation and multiply by y1. So is x square y double prime 2 multiplied by y1 minus x times x plus 2 y prime 2 multiplied by y1 and plus x minus 2 y2 multiplied by y1 equals 0. Now I'm going to add. All you can do is you can add these two equations. So you add each term and you can see that this last term get cancelled, and for the first term I am getting, what I'm getting is x square times x squared times y double prime 2 y1 minus y double prime 1 y2. So I'm going to just write from bottom to up, so it doesn't matter. So you take those two terms and take x squared out. Similarly, here you also take x times x plus 2 out, and then you get y prime 2 y1 minus y prime 1 y2 equals 0. Okay. So let's leave it here. Maybe you can call this equation 3 and leave it here and see what those coefficients of x square and x times x plus 1, like y double prime 2 and y1 blah blah blah. So those coefficients, what do they mean to us? So let's take a look at it. So now from the Wronskian, so Wronskian of y1 and y2 will just be the determinant. So you write in the first row y1 and y2, and in the second row y prime 1 and y prime 2. Okay. So then calculate the derivative. So you get y prime 2 y1 and minus y prime 1 y2. Oh, and you see, oh, in equation 3, in the last term, what you have is nothing but the Wronskian. So you can replace this term with w. Okay. Now let's see what this one, and I don't know what this one, so I'm going to think that whether this one is a derivative of Wronskian or not. So let's first calculate. Wronskian is a function of y1 and y2, but y1 and y2 are functions of t, or functions of, in this case, x. So I'm going to differentiate with respect to x, which is w prime. So excuse me, I differentiate here. So if I differentiate here, I will differentiate term by term. So the first term will be a product rule. So this is y double prime 2 y prime plus y prime 2 y prime 1, okay, minus the second term similarly y double prime 1 y2 plus y prime 1 y prime 2. And you can see that this y prime 2 y prime 1 appears positive and negative because of this negative sign. So you get y double prime 2 y1 minus y double prime 1 y2. Oh, and you can see that this coefficient is the same as this coefficient. So you can replace in those quantities in equation 3. If you look at an equation 3, then now you get x squared w prime minus x times x plus 2 w equals 0, and you get a separable equation. So you separate, and then you can solve it for w. So if you separate, you get actually x times x plus 2 divided by x squared dx equals 0. Okay. So maybe you manipulate a little bit the second term before you integrate. So the second term will be x squared by x squared, which is 1, and then 2x by x squared So it's 2 over x dx equals 0. Okay, so this integration is not difficult. So you get ln of w minus here you get x plus 2 ln of x, and on the right hand side you have a constant. You can write it doesn't matter, any constant, say c1. And if you manipulate in the left hand side, you can see that ln of w and ln 2 negative 2 ln of x. So negative 2 ln of x becomes ln of x to the power negative 2, or x to the power negative 2, or x to the power positive 2 and with a negative sign outside. So if you write ln of plus ln of x to the power negative 2, then actually you get ln of, you can combine them together, and then you take x to the right hand side, so x plus c1. Once you write this, you see that it's wx to the power minus 2 equal to e to the power x times e to the power c1, and which you can write as a constant. So here c is e to the power c1. It is just, we're doing a lot of, about this simplification. So this is not a calculation, this is a new symbol. So w x to the power minus 2, w equal to c x squared e to the power x, and this is your Wronskian. Now you see that in the Wronskian you have a constant, and earlier when you calculated Wronskian you didn't have a constant. So this is a constant of integration, so this can be chosen just one, and you can just simplify it. Wronskian w is x squared e to the power x, which is not that important. The most point is that to calculate the Wronskian, whether we don't know the solution. So if we know the solution, we can form the determinant, and then we can simply calculate the Wronskian. If we do not know the solution, then we assume that y1 and y2 are two solutions, and then we do some algebraic manipulation to convert the differential equation into a first order separable equation. So this example is not only about illustrating how to form the Wronskian. This is an example to illustrate how to convert the second order differential equation into the form of a first order differential equation that also can be manipulated and can be used. Thank you very much for watching. If you have any question, do not hesitate to contact me. Thank you.